Professor Brynn, please.
Gosh, well, thank you very much for that very nice introduction. I hope you can see the screen now. Good, I see nods. Yeah, so first, well, it was my pleasure. It is absolutely my pleasure, and thank you very much for asking me to contribute to your group. I've been on the periphery of the solubility people for many years. I've known Clara for a long time, and I've occasionally helped with various projects, but I wouldn't say I'm a solubility person. But somehow my work hopefully will inform yours. I'll talk today. I won't go on for an hour, so that's good. I think when I thought what I was going to say the other day, it didn't take quite so long. So, and I should say excuse me, I'm recovering from a cold as well. So, having had COVID a long time ago, but it's terrible. It's winter here. You've probably heard, you know, Sydney is flooding and whatever. But luckily, where I live near the coast, we're okay.
But look,
okay,
here it's 42, so we are like in the middle. It's okay.
Oh yeah, it's that's right. It's 11 here, so we could meet halfway and be happy. So thank you for letting me join this group. You see your various symbols. That's the University of New South Wales. Of course, IUPAC. That's my Royal Society, which is the oldest learned society in the Southern Hemisphere. And this is a copy of a painting that was done for a prize, a big prize in Australia, which I managed to get into the finals. They usually do politicians and pop stars, so scientists was unusual. And it was obviously a long time ago when I looked quite different. So let me tell you what I'm going to be going on about today. I am going to kind of work through the uncertainty bit, and I'm sorry if I repeat something that Ala will do in the next talk, but it'll be good to see it perhaps first here and then so on. And I should also say that I don't know my audience, so really I've got a horrible feeling I'm going to be speaking to some people who know it all and therefore will be bored, or it'll be so complicated for the other half of the people that you'll get unhappy and realize that all this uncertainty nonsense is just as you thought. But hopefully there'll be somewhere in the middle that will take something from it. So I'm going to talk round a bit on the philosophy of uncertainty. We use the word error for so long, and now we use this word uncertainty. And what does it mean? And where's it come from? That will lead me into how you do an uncertainty budget, and I'll kind of go through the GUM bottom up as it's known procedure in somewhat briefly, but hopefully I'll get through all the steps. I'll say something about regression because there's one or two things in my work with Earl Waghorn that I actually became quite interested in, the business of whether you do weighted regression or not, whether you regress logs of things rather than the things themselves in a non-linear way and so on. So I'll talk about that because that might be of interest to some people. I'll give a couple of examples. I wrote a tutorial in the Journal of Chemical Thermodynamics a year or so back, and I'm going to lift a couple of examples from that. There's a lovely paper which I think Clara was on, and the late Hans Gamsegger, who that's got some lovely points in it, and I'll draw your attention to that. But what I've been doing recently is, again, what most of the SSED do, and that is work out consensus values given already published solubilities or thermodynamic parameters or what have you, hopefully with their uncertainties. And it is not totally simple how you combine half a dozen values together. And I'm going to work through that, and I'm going to give you an example, in fact, one of Earl's problems that we've been working on, and then I'll stop, and by that time I think everybody will be totally tired. In the slide, I say all the material here will be available, so please have a look at the PDF. I can't help putting my own stuff in there because that's easier. So I wrote a book on quality assurance quite a long time ago now, but it's a lovely book. I like it. It's won a prize for it. I did quite a nice review of linear calibrations in the Analyst, again quite a few years ago. Managed to get the middle equation completely wrong, and the referees didn't pick it up, so there's a nice erratum that goes with it. And then the tutorial that I published a couple of years ago. I'm glad to see that others from NIST, I approve of them hugely. When I was on the GUM committee with Antonio Pasolo, we became very good friends, and I think NIST is really up there these days, and so I'll point you in the direction of a couple of NIST resources for doing uncertainty budgets, which I won't talk about, hopefully I will, but the consensus machine I will speak about. Then, of course, there's the GUM and the VIM, more of later, and finally the Eurotech, excuse me, the Eurochem SciTac guide, which I will suggest is actually a more readable form of the GUM, and is something that perhaps you should all get rid of. You should all download and work on. Okay, where does uncertainty come from? Well, uncertainty comes from the BIPM. This is the Pavilion de Breteuil in outskirts of Paris, where the BIPM lives, and they. The photo I've taken, I went there at IUPAC's expense for about 7 years while I sat on the GUM committee, and it's a lovely place. If you can get a gig there, please go, because they have a fantastic wine cellar. It's a lovely chateau, and it's a delight to spend time there. So if you can see my screen already, uncertainty might be thought of as to stem from 1977, and this is quoting from the foreword of the GUM, recognizing the lack of international consensus in the expression of uncertainty in measurement, the world's highest authority, blah, 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 decided they'd do something about it. And they got together a bunch of chums that obviously involved people like ISO, but also IUPAC and IUPAP and so on was in there from relatively early on. And they all got together. It was decided to let ISO do the organizing, and so a working group created a technical advisory group on metrology, TAC4, established its working group 3, which originally had people from the BIPM, ISO and IEC, and also the International Organization for Legal Metrology, which is kind of interesting that they were the people very early on that worried about how uncertain, if you like, or how certain they were when measurements were presented to the various courts of the world. And this is something that I do a lot of. So the first GUM, the first Guide to the Expression of Uncertainty in Measurement, comes out in 1995, and by now it's got more or less the final group of people who are going to work on it since then. The BIPM, IEC, ISO, IUPAC, IUPAP, our colleagues from the International Union of Pure and Applied Physics, and OIML. And in fact, a couple of years later, ILAC, the International Laboratory Accreditation Lot, they join us as well. And so, and in fact, because of the international nature of it all, and we didn't want it to be owned, as it were, by one organization rather than another organization. This thing was created called the Joint Committee for Guides in Metrology. Its home is at the BIPM. BIPM provide the rooms, as we've seen, the secretariat and so on. And it's made of these 8 organizations, these 7 plus ILAC. Each organization sends 2 people along to the meeting. So I was one of the IUPAC representatives. and it has a chair. Walter Bish is the GUM chair at the moment, and away they went. So the GUM that you will download and look at and we'll talk about today stems from 2008, which is the 1995 GUM with quotes minor corrections. And this is the one that we're going to talk about. The VIM came out a few years later. There was an attempt to update the GUM while I was there, and it failed. None of our organizations would have a bar of it. So what's actually happened in the period since the GUM came out in 2008 is that we've made supplements. So you can see them listed there. I had quite a bit to do with the conformity assessment 106. And I noticed since I've left the organization, the GUM 6, they've now slightly changed their way of numbering their supplements on measurement models. And so when we talk about the GUM, it's not just the 2008 document, it's plus the supplements that actually fill out the use of it all. However, having said all that, the GUM is written by metrologists and essentially written for metrologists. I think, and perhaps the feeling has changed in the few years since I've not been on it, but on the whole, they rely, the GUM people rely on other organizations interpreting the GUM to the outside world. So NIST has done a lot of work, of course, and Eurochem SciTac, I mentioned their guide, and they've produced a lot of useful material on uncertainties. And indeed, most recently, the uncertainty of qualitative analysis, which of course I won't go into today. But that's just a bit of history in case there's some students out there just wondered where it all came from. And this is the logo, that metrologia, I presume, and you know, I'm not sure what the two friends are. They look very odd to me, but anyway. So let me kick off then by asking you to contemplate the concept of a true value. You see, you talk about trying to measure solubilities. Well, what actually do we mean by that? What is a solubility? What does it mean in a kind of metrological sense? And so a quantity intended for measurement, which we call the measurand, okay, is by GUM, thank goodness, considered to be a real feature of nature. It actually exists. You are measuring something that hopefully is out there. And it is characterized by an essentially unique true value, i.e. there's one value that you're trying to find. But of course, the big problem that you have, and I have as an analytical chemist, is that true values are unknowable. If we knew the true value, we wouldn't be asking us to measure it. We'd know it. And of course, there are some values that we do know by decree, by universal acclaim, as it were. So the true value isn't known. That's as I said, truism. The GUM calls an error the difference between a measured value and a true value. I say the GUM does because the VIM doesn't. And if the true value isn't known, then the error isn't known. And so the whole argument about trying to estimate errors is this problem of not really having the thing that you're trying to say something about is not knowable. Okay, you say, well, the thing you're trying to measure isn't knowable either, so we're all in the same boat. But in fact, you can say things about the thing you've measured that are true, that are exact, and usually statistically manipulated. But we're going to tell you something about your measurand by doing this uncertainty nonsense. So, and so if you can think of it in terms of states of knowledge, we start off by not knowing about the measurand. Well, we know a little bit about it. We know it's probably somewhere between 0 and some number, but clearly not well enough to satisfy the folk who are going to use our tables of solubilities or what have you. So we make a measurement, and that measurement improves our state of knowledge of the measurand, the value of the measurand. And the measurement uncertainty is a way of explaining that state of knowledge, how good that state of knowledge. A small uncertainty means we're more certain about the value that we're trying to offer to the world. And interestingly enough, the laboratory of the government chemist a few years ago suggested that we actually should turn it on its head and actually define measurement certainty, not measurement uncertainty. And in fact, because they said the point about if you have a good uncertainty budget, you actually know more about the system than if you didn't have an uncertainty. So it's actually improved your certainty having an uncertainty. And therefore, what we should be doing, and everybody thinks of uncertainty is that we just don't know. And that somehow reflects badly on us all. So why don't we call it certainty, and everybody will be happy? Well, you know, we all sat around and said, what a lovely idea. And there's no way that we're going to change measurement uncertainty to measurement certainty. But if you think about it like that, it's kind of interesting. Okay, so what is uncertainty, measurement uncertainty? The GUM defines it in terms of something about a measurement result, non-negative parameter characterizing the dispersion, spread, of the quantity values being attributed to a measurand based on the information used. Okay, now, so the first thing you know is that the GUM's first go, and this is in Vim as well, at measurement uncertainty, is nothing about the true value. It's not telling you anything about the true value at all. It's telling you about what you've measured. It's the dispersion of the values coming out of your measurement, which is a bit of a cop-out, really. And in fact, in the GUM itself, they then have to kind of qualify this, and they say a couple of other things in the text. So it's a measure of the possible error in the estimated value of the measurand as provided by the result of a measurement. So that statement kind of gets in the word error, but more or less says the same thing. But finally, they say, okay, it's an estimate characterizing the range of values within which the true value of a measurand lies. Well, that's really good, because that's what you want. Okay, that's what you want to be able to say. And if you've corrected for all systematic effects, then your measurement result with its measurement uncertainty is both the dispersion of your measurement results, but it is also an estimate of the true value and a range in which the true value lies. And very interestingly, the Vim 1984 actually defined measurement uncertainty as that. And it was changed in the latest Vim and GUM to say what you see at the top of the slide. So there's a whole philosophy behind this, and you don't need to get into it actually, but people spend a lot of happy hours arguing the toss about true values or errors or what have you. I don't know if this is any use. I'll perhaps go over it reasonably quickly. A PhD student of mine a few years ago did a thesis on worrying about bias and errors and all kinds of things. And one of the things that you find when you get into this is the concept of so-called top-down versus bottom-up. And you're told that somehow top-down is by doing lots and lots of experiments and taking a standard deviation, and therefore you don't have to mess around with all this nonsense with individual equations and quantities and what have you. And what this kind of slide is trying to explain to you is how this also is a continuum, how you can turn bottom-up quantities into top-down estimates or dispersions or what have you. So that you start down you do a run in a lab, and it's got you get a value. It's clearly got an error associated with it and some dispersion. But you do it a lot of times, and you take all of those results together from your lab, and you get a consensus value, if you like, from your laboratory, and that has somewhat wider dispersion. And another lab might do the same, and they'll get a slightly different value with their own standard deviation and what have you. But then if all the labs in the world get together, then you can perhaps finish up with some big envelope of all the results that you can possibly have. So this is now the ultimate in top-downness. And you would hope that the result that you've got is the value of the measurand that you're seeking, assuming that there's no underlying bias, underlying error. So perhaps if all the labs in the world use the same measurement method, and it just happened that measurement method gets it a bit wrong one way or the other, then it will still get it a bit wrong one way or the other. But ultimately, you think if you do enough, if you allow enough of your variables to vary, then you can use a standard deviation to give you an idea of the uncertainty. And you'll find in the GUM, they try and make this distinction between so-called type A effects, which come from random and are produced by getting a sample standard deviation or what have you, which will be ultimately some kind we used as a measure of your uncertainty. And then there's a whole bunch of other things which they call type B, which include systematic effects. And we'll see there's going to be one or two others, but I'm not going to get into that because hopefully somebody will cover that in a future talk. So I'm just going to spend a few moments essentially explaining how you go about getting a measurement uncertainty budget together. And whether you'll be able to do it at the end of this, it's unlikely. You'll have to read more, try it on your own problems and so on, come back and kind of talk to us. But this is the way that the bottom-up approach kind of works. And I've taken it from unashamedly from the Eurochem guide, because I think that actually is a much more readable document. 5 steps to enlightenment children, 5 steps. The first thing is you define the measurand, and that is possibly almost the most important step. You've actually got to write down what it is, the quantity you're trying to measure. Just sounds obvious, it's the solubility of this and that or whatever it happens to be. But honestly, the number of times that I see people and my students and so on kind of assume they know what they're measuring, but then somehow measure something else because they never really thought about it. So you define your measurand, the quantity intended for measurement. You decide on the measurement model. You write, of course, this is all in the background because you've already done this and you know about it, but this is what you kind of do. So you write a measurement function, which gives the relationship between the measurand and the input quantities. Y equals a function of a whole bunch of x's. You allow for corrections, because they're not going to get done by any kind of statistical procedure. And you have to decide at that point how you're going to treat things. So for example, you might ignore a temperature effect, or you might correct for a temperature effect. You're delivering a volume. Obviously, volume depends on temperature, and the pipette is certified at 20 degrees centigrade. You might, on the one hand, say, well, the lab's near enough 20 degrees centigrade, I'm not going to worry. Or you might actually measure the temperature and apply some kind of correction, and that correction will have its own uncertainty. So you have some choices to make on the way. If you do a weighing, if you're doing very accurate weighings, then you have to worry about air buoyancy corrections and so on and so forth. More of that, again, perhaps later. Second, you take your measurement model, which could be as simple as this from the first in the Eurochem guide, which is just making a solution of cadmium by dissolving a mass of whatever cadmium salt in a certain volume. The salt that you're using has a purity. Don't take, again, this is for students, just don't think because it's got a nice fancy label on the bottle, it's 100% pure what it says. If you're using it to calibrate something, you will need to use some kind of reference material that comes with a known purity and an uncertainty. So these are things called Ishikawa diagrams. As far as I can see, the only thing they're good for is when you're writing the paper and then you work backwards, having done all the uncertainty budget, and then you go back and work out what you actually did, and you write it up as this rather clever Ishikawa diagram. So the one on the right is, I say, out of the SciTech guide. The one on the left is a paper I wrote about CO2, total carbon dioxide in racehorses. Turns out that if you feed a racehorse sodium bicarbonate solution, it raises briefly the CO2 content of its blood, and that suppresses lactate, and that makes it run further. Or so is the conventional wisdom. So racing authorities measure plasma from selected horses, and there's a limit of 32 millimolar of total CO2. And this is from this paper. You can, if you want to go to it, it's actually called a GUM compliant uncertainty budget, probably one of the first in this area that was published. So you can perhaps go through that if you want to. So identify uncertainty, quantify the uncertainty components. You'll certainly get more of this in the next talk. And I'll just mention a few. Obviously, if you happen to know a population standard deviation of something, you can use that as an standard uncertainty directly. The GUM that was going to be changed would have had this formula in it. So if you have a sample standard deviation from N data, we are now going to recommend that you use this scaled and shifted student t distribution, which means that the standard deviation of the mean, S on root n, is multiplied by this term, n-1 over n-3. So you've got to have at least 4 data points to do this. And we say in the text, if you don't have 4 data points, then you shouldn't be really taking a standard deviation. You should be looking to some other way of determining the uncertainty. And then often you'll come, a piece of equipment will come with a plus or minus, like a balance weight or the volume of a pipette. That plus or minus isn't a standard deviation or 2 sigma or anything like that. What it is we guarantee that anybody who buys one of our pipettes will, their pipette will deliver somewhere between the nominal volume minus A and the nominal volume plus A. But we don't actually say it's the nominal volume, interestingly enough. So that turns out to describe a rectangular distribution, and you can turn it into a standard uncertainty. U, by the way, is this thing called standard uncertainty, and we'll be talking about that a lot, as the half width divided by the square root of 3. And then there's a whole bunch of other things you can do. There's triangular distributions, other distributions that might come up, and so on. But these 3 probably will suffice for the majority of things you do. Okay, then you've just got to stick them all together. And this is where the kind of calculus fun starts. So given your measurement model, and which y is the output variable, given a function of a certain number of input variables, multiplied, divided, logged, whatever. Okay, we've decided in the previous step, we've worked out the uncertainties of each of these little bits. And now all we have to do is to put them together. The so-called propagation of error or propagation of uncertainty is a kind of first order approximation of Taylor series or whatever, and it comes out looking like this. Correlation is the big bugbear of anything that we do. Most people ignore it, and often that's kind of bad, because correlation has a very big effect on things like a straight line graph. The slope and the intercept are correlated, and you cannot ignore that if you decide to work with a y equals a plus bx, although we'll see a way around it in a moment. So, but if your x's are truly independent, then you can ignore any covariance matrix. That's what this u over here is. And you finish up by having this thing called a sensitivity coefficient, which is the differential of y with respect to the variable you're concerned with. It gets squared and multiplied by the square of the standard uncertainty of the variable. If you look at it, that kind of makes sense, because you're going to have an x squared on the bottom and an x squared, as it were, in dimensional terms on the top. That will cancel, and f as the dimension of y. So you'll be getting a number out that has the dimension of y, which is what you want, because you want the uncertainty in y given the uncertainties in all the x's. So this is the approach that the GUM uses, so-called propagation of uncertainty. And so the argument goes that once you've got these standard uncertainties, whether from standard deviations or from
I believe we have
using these standard deviations, these standard uncertainties. And then finally, do we have any problems? I've got my internet connection is unstable. So
for a moment, but then it came again. It's normal now.
Okay.
Again. It's only for a few seconds.
Okay, good. Thank you. Yeah, my warning's gone away. Long way from Australia, you know. Yeah, lots of satellites and things. Anyway, and so finally, at the end of all of this, we, because our clients, as it were, might not want a standard uncertainty, although standard uncertainty, perhaps with degrees of freedom, is all they need. They often like the idea of a 95% coverage interval, or whatever it happens to be. So we expand our combined uncertainty by a factor, which is usually looks remarkably like 2. And then we will be able to quote at say a 95%, and then we report the result. Please, you should always say what plus or minus means, because plus or minus can be anything from 1 standard uncertainty, especially if it's rather large. People don't like multiplying it by anything because it looks bad enough already, or it is 2 times, it's a 95% confidence interval, or it's one of these things, like I said, with the pipette, which comes as 10 mil plus or minus 0.01 of a mil. That plus or minus isn't any of those. It's actually a range, as I described just now. So you cannot get away with just writing plus or minus. You have to say what the plus or minus means at some point in your paper. You know, you don't have to do it for everyone. If you say plus or minus in this paper means a 95% confidence interval, fine, you know. So you have to, so this is a gum-like statement that they try and get everybody to use. Solubility of sucrose is 200 plus or minus 5 grams. And again, just remember things like significant figures. Yeah, your uncertainty should be quoted to 1 or 2 significant figures, certainly no more, and your value should be rounded to the same number of decimal places. Again, this goes for perhaps to students who use spreadsheets that seem to give them more numbers than they can cope with. So where the reported uncertainty is an expanded uncertainty calculated using a coverage factor of 2 gives a level of confidence approximately 95%. Don't forget, uncertainty, this is an uncertain business. You know, the uncertainty is uncertain. So don't get hung up on saying, well, it should be 1.96 really for 95%. Doesn't matter. 2 is good enough, and about 95% is a sensible thing to say. Okay, so let's just keep a perspective on this. Okay, I'm going to spend a couple of minutes talking about regression. Okay, as I understand now, I learned from my friends that we often present data as a regression, say as a solubility regressed against temperature, which I'll be giving an example of later, or some augmented Van 't Hoff kind of job where you're adding there's a bit of curvature, so you're adding a few more terms. Again, for the perhaps for the students, but it may come as a shock to you that both of these equations are linear equations. When we talk about linear regression, we don't mean linear in the variables, we mean linear in the coefficients. Okay, so think about, you know, if you do this in a spreadsheet, you'll have a column that's 1 over t, you'll have a column that's t squared, and LINEST or whatever you're using won't care what they're actually, where they've come from. It'll do a nice linear regression on that. So when we talk about linear regression, linear in the coefficients, not in the variables. And so we often take the log of, say, a solubility and regress it against 1 over t or something like that. Okay, now we will tend to use ordinary classic linear regression because we've all got Excel and we've all got spreadsheets and we've got away with it for years. Okay, what do we assume though if we use a classical regression? The first is that we assume that the function's correct. We're not testing the function. Van 't Hoff did that years ago, or whoever came after him. We're assuming that it's absolutely correct. Now that of course is not necessarily a true statement, and if it's not, you need to worry about it. Because what we're now going to say is that any deviation off the fitted line is due to uncertainty or error in the y value only. So ordinary linear regression assumes that the x values are absolutely correct. Again, if that's not the truth, that you've got to worry about it, and you've got to do something like error and variables model, or there's a whole bunch of ways of coping with it. But if you stick to ordinary linear regression, you're putting all your uncertainty eggs, if you like, in the one basket of the Y value. Okay. But once you've done that, you fit it, and you can calculate both values from your fitted regression equation and uncertainties, which I'll explain on the next slide. When I got some data from Earl some months ago now, we've been at this for rather a long time, what I saw was the traditional Van Hoff isotherm, so log S plotted against 1/t. In fact, we showed that for his data was more than enough. You didn't need to add any extra 80 squareds or anything for the particular set he'd got. You can test this by ANOVA and so on, and it's always a good idea not to use unnecessary variables, as it were. Add another term, it's bound to fit at least a little bit better, but is it significantly better, statistically better? Okay, so we fitted, and the first thing I said was, well, this is a problem, because if the model says that the Y value is normally distributed, all the errors are in Y and they're normally distributed, I should say, and they're independent of X, homoscedastic, then log S isn't. So you can't have it both ways. You know, if we think that your solubility measurements all have the same uncertainty, or are picked from a distribution having the same variance, then you can't take the log and expect the same when you do your regression. So I got us to use nonlinear regression, which you can still do in dear old Excel using Solver. The uncertainty model then becomes a bit more difficult, but actually to just fit S against T, and away we went, and we got answers and so on. But later on in our discussions, I realized that one of the interesting things about a log is that if you fit a log to a linear regression, okay, no longer is the log taken with a constant variance from a pool of values. However, it's a constant relative error. So, of course, because when you differentiate a log, you get 1/the thing, right? D log X is 1/X. So it turns out that the uncertainty in log S from our regression is actually the relative uncertainty of the solubility. And that seemed to me actually a lot better. I mean, it'll be interesting in the discussion if Earl's had some thoughts on this, but when I listen to Earl or other people, they often talk about the uncertainty being 1%, 2%, whatever it is. Now, that's not a constant, okay? It's a percentage of the value of the thing you're measuring. And of course, in most of analytical chemistry, as whatever you're measuring gets bigger and bigger and bigger, the uncertainty gets bigger and bigger. And in fact, for many measurements, the relative uncertainty is a much better thing to take than the straight uncertainty that you get from an ordinary linear regression. So that was kind of an interesting moment for me, and I hadn't thought about it before I did this work with Earl's data. So I think at the moment, what I'm suggesting then is you carry on with your Van Hoff isotherm and realize that the uncertainties you get out are relative uncertainties, but entirely useful, and you should go for them. If you don't want to do that, if you want to stick with the nonlinear regression, or if you have this idea that your uncertainty grows with the values that you're measuring, then you can always do a weighted regression. Essentially, with the kind of thing I've been discussing, if you have a bunch of standard deviations from repeated measures or what have you, and they seem to be going up as the value of the solubility goes up, then you can always do a regression that's weighted by 1/the variance of your data. Okay, there's good statistical arguments for that, which I won't go into. However, having said that, again, I've now done quite a bit with that, because I was asked a similar question in my own university, and I worked on quite a lot of data. And every time I've done a weighted regression, I've got virtually the same answer as I did with a non-weighted regression. And in fact, the uncertainty didn't really change very much. Now, there's obviously cases where that can't be, that has to be right, that where the you have to apply a weighted regression. But I've now not so fast to do weighted regressions. If everything with unweighted things seem to kind of be sort of okay. And I guess what I'm saying is, if you have an enormous range of results that you're trying to fit, then obviously you're going to have to take account of that increasing thing. But if you're doing it over a relatively small range, some of the examples I'll show you, then you really don't have to bother. Okay. I'm not going to say much about this slide. If those who want to read it can, but it shows you how to get uncertainties. So we've fitted log S against 1 over t. We've got the coefficients A and B from our fit. And the question is, if I now plug in a temperature, I recover my value of log S, what's the uncertainty in log S? Okay, and that's what I need to know, of course. And the answer is, what you need to know are two numbers: the standard error of the regression, which is called SY on X, and I think Excel calls it SY on X, and you need the standard error of the slope. Okay, what happened to this intercept, you ask? Well, we got rid of it. So in fact, instead of writing log S equals A minus B over T, I'm writing log S minus the average log S is equal to minus B into 1 over T minus the average T. Remember, T doesn't have any uncertainty, so we can ignore that. B will have an uncertainty, and we measure that by the standard error of the regression. Log S bar has an uncertainty because it's the average of my Y values, and we know that Y values have got uncertainty. But the average of the uncertainties in the Y values is given by this error of the regression, because that's the assumption made when we do an ordinary linear regression. So the bottom line in all of this is that you just need those two things from the linear regression: the standard error of the regression and the standard error of the slope, and you can get an uncertainty from the regression. And please note the caveat at the bottom of this slide. This is the uncertainty contribution from the regression. Okay, it captures variability in all of the Y's that we've got, but it's not necessarily the whole story. And when you're doing an uncertainty budget, you have to think hard about what else you need to put in. Also, if we just go back to this expression for the uncertainty up here in the middle of the slide, notice that in the middle of your regression, 1 over t is going to be about the average, right? 1 over t of the average of all your 1 over t's. So this second term is going to be 0 or near 0. So in fact, very simply, the uncertainty in log S is just given by the standard error of the regression squared divided by n, and that's the square of the uncertainty. So it's not rocket, it's not that hard. You can do it in Excel. Okay, that's all I wanted to say about the just the generalities of uncertainties, uncertainty budgets, and so on. I realize I haven't told you actually how to do an uncertainty budget, and everyone is going to be a little bit different. And I think that's what worries people, because do I include this, do I not, and so on. And I hope as you get more talks in this series, you'll get enough examples where you'll be able to kind of, oh yeah, you know, somebody said that's what you have to do in this situation, and so on. So I'll give you a relatively straightforward example from some work that I've done. I work with a materials scientist called David Young, and he's very good at measuring oxygen solubility in alloys. He's much sought after in the world, apparently, and so on. And I was brought in to help him with essentially the statistics of some experiments he was doing with a student. And this is a very simple example, but you can have simple examples, but it was solubility, you see. So I thought, solubility, that's what you guys are. So we have an oxygen mole fraction in an alloy, and we measure it at 1000 Kelvin or something. And we use some kind of infrared detection method using an instrument called a LICO. I wouldn't know one end from another, but you get numbers out of it. And when they did this work, they did an awful lot on the uncertainty of the measurements from this ear, from this ear instrument. So we have a pretty good handle on an individual, the uncertainty of an individual measurement from the thing, from this instrument. Ooh, that's interesting. Anyway, so my measurement equation, my measurement function, is the thing I want, the mole fraction of oxygen in the alloy, is what I measure using this instrument, minus some small impurities that come in because I've got aluminium and titanium, and that contaminate the iron and the nickel, and they pick up oxygen and they finish up with oxygen that I'm measuring, but isn't actually part of the iron nickel alloy. So I have to have this kind of correction. And that's all it is. Ah, but wait a minute, we all said. What about the temperature? Because we've got a furnace roaring away at 1,000 Kelvin. What's the uncertainty in the temperature? And does that have an effect? So this is an example where we don't have temperature in the measurement equation, but it's something we have to worry about. Okay, we see the next slide, and this is where I learned a lot of things about solubility of oxygen in alloys and so on. So apparently there's something called Sievert's constant. I'd never heard of him, of course. He's probably never heard of me. Probably dead, perhaps. Anyway, which links the solubility product and the solubility to the partial pressure of oxygen, and is given by this constant. But this constant is a function of temperature. Seems reasonable. That's okay. So we spent a lot of time, and again, I'm going to let you read through this if you want to later. But we knew the uncertainty in the various free energy parameters, the enthalpy and the entropy. We knew that we could hold the temperature to about plus or minus 3 Kelvin. Notice this is this idea of a range, so within 3 Kelvin either side of the nominal temperature, we think we're okay. So we call that 3 divided by √3, rectangular distribution. So our uncertainty of temperature is 1.7 K. But then we have to feed it into this bunch to get an uncertainty in X naught, given an uncertainty in the temperature. So I'm not going to go through the maths, but feel free to work it out for yourselves. Again, because there are logs involved, we finish up with X naught itself in the expression. And the bottom line, after messing around rather too much, I should have done this quicker than I in fact did at the time, that there's about 3% relative standard deviation uncertainty in the effect of the temperature. Now, I'm going to show you numbers that are so far more than that. We promptly ignored it, and so that is now not going to be considered. But it's a very good example of how, when you're doing an uncertainty budget, you think, what about the temperature? What about the purity of this? What about? And you have to really tick them off. It might be that you're good enough to say, oh, look, nobody worries about temperature. I had to go through the maths and persuade myself that it was okay. But that was nice. It was a page in the student's PhD thesis. So this is the final answer. Applying the propagation of error, it couldn't be simpler. There are no coefficients to worry about. So the square of the uncertainty in my mole fraction of oxygen is simply the 4 things that I'm worrying about, the uncertainties in them squared. And this is what I finished up with. Again, the answer actually is not much different from if I just took the original LICO thing. But again, we didn't know that at the time. And in fact, the fractional difference is a little bit more. So it's 26%, whereas it's only 23% in the original value. So, I mean, these are good results, I'm told, by my colleagues. I don't know. So this is the bottom line. So you finish up writing tables like this, where you write your various quantities that you're interested in. Usually the thing that you finally want is at the bottom. the things that are in the measurement equation are down the side. You write the value of them, you write their uncertainty as you've calculated by the various means I've just told you, and you often give a relative uncertainty because that's kind of useful to just have a look and see if it makes sense. Okay, that's an example, and a very straightforward one in terms of the basic equation, but not straightforward in the way that I approached it and so on. Okay, I've used 48 minutes and I do apologize, Simo, and I will now try and speed up, but I will possibly go on a bit. Talk about consensus values. You've got a number, it sounds a simple problem. You have 6 values from different laboratories, different publications, 6 uncertainties. They all purport to measure the same thing. What value shall I put in my consensus value, if you like? Okay, I'm going to give you 4 ways of doing it. Way number 1, which is possibly what most people do, you use a weighted mean. So because each value has a different uncertainty that comes with it, I suppose there's a 0th value, which says ignore all the uncertainties because we're all coming from the same population. Let's just take the mean and the sample standard deviation of the n values that I've got. Ignore their unpublished uncertainties. I've got 6 values. What would I normally do in my lab? I'd average them, take the standard deviation. Thank you very much. And that's actually perfectly okay if you assume that all the labs are blindly picking from the same, exactly the same distribution that exists in the firmament, as it were. Now that's not going to happen. That's not happening, is it? So method 1, let's take account of their own confessed uncertainties. Now, of course, critical evaluation of data. Do we actually, somebody gives a very small uncertainty, well, do we believe them? And so on. But that's for another time. Weighted uncertainty is, weighted values are fine. These are the expressions for the weighted average and the weighted, excuse me, the weighted uncertainty. The weights we use invariably are 1 over the standard uncertainty squared. And again, you can do all this in a spreadsheet and you get answers out. Don't forget, because my friends in solubility, I know Earl was worried about this, that when you take all of these values from around the place and you work out a consensus value, an average of some sort, however you do it, and an uncertainty of some sort, the uncertainty is always going to be smaller than any of those, because it's standard deviation of the mean. You're dividing by root n at some point, whether explicitly or implicitly by dividing by this term here. So in a way, I feel there's a little bit of guilt coming in from my colleagues that somehow how can they offer a smaller uncertainty than any of these labs who actually did the hard work of doing all the measurements? Well, statistics is like that. If you take more samples, you get a better answer, you get a better knowledge of the thing you're after, the mean. And as long as you keep your nerve, you can play that game. However, having said that, the weighted uncertainties are usually too small for people's liking. So I discovered this 2 people, De Simonian and Laird. They published a paper which I should have put in here. I'll kind of throw it in another copy of this at some point. And it addresses this thing called dark uncertainty. I'm very good friends with Steve Ellison, who's at the laboratory of the government chemist. He's a really good applied statistician. And I absolutely hate him for being one of the people who invented the concept of dark uncertainty. So it goes like this. You have all these values and they've all got their own uncertainties, but just looking at them, the actual the values are way much different than anybody's uncertainty would ever give credit for. That can't be right, can it? And this idea of dark uncertainty is there is uncertainty between the laboratories that's lurking there, like dark matter in the universe. It's a lovely concept, and it's if you have to teach this, it just It's obvious when you talk about dark uncertainty. And of course, the problem with dark uncertainty is that each individual lab doesn't know it exists. And so they can do their experiments as much as they like, but they will never probe the difference between what they're doing in another lab. Now, you might say if they do a bottom-up gum uncertainty budget really, really properly, they'll kind of work out what the biases, what the systematic errors are that are moving their values away from each other. But in practice, they won't. So Desimonian and Laird come up with a process of taking our measurement model, which usually stops here. We have a true mean and a normally distributed variance around that from our measured values. And they're adding a single variance that's common to all of the laboratories that represents our estimate of the dark uncertainty tool. So how do you do it? Again, I'm not going to dwell on this. It's relatively easy, but you do this in a spreadsheet and you'll get it wrong about the first 5 times because you'll forget to, you'll square these before you multiply them together, or you'll add them up and then you'll square them, and you should have squared them before adding. But if this is correct, and you can use your data that you already have, your weights and your x's, to give you an estimate of this dark uncertainty parameter tool. And then you can put it back in and get a weighted dark average, and more to the point, an uncertainty. And we'll see some examples of that. In a sense, nearly finally, although I do have something called linear pooling, linear opinion pooling, taken from the social sciences, when you have lots of questionnaires and people do this, that, and the other, and you want to kind of bring them all together. And really, you don't have a statistical model. You cannot, in all honesty, say that this is from a Gaussian that's blah, blah, blah. So, which we do with Desimonian and Laird and weighted, and weighted, whatever it is. So in linear pooling, we're not making any assumption about the form of the distribution of our final result. And in fact, all we're going to do is take each bit of information separately, a mean and a standard deviation, or as a variance. We're going to work out a distribution that represents, and we're going to literally add them up. And what you get is a very lumpy overall of these, and I'll show you some examples in a minute. You can work out, you have to do it kind of numerically, you have to work out where the 95% confidence interval is, where you can take the median or the mean of all of those values, and that's fine, and away we go. And it's called, and I'll show you some examples. It gives often the largest uncertainty, which again might satisfy some people, probably not necessarily the way that we ought to go, but it's available if you need it. Finally, actually, I did throw this in because the Gamsegger example is one where he does all the sums and then he says, well, I'm going to ignore all of that. I think the uncertainty is 10% or whatever it happened to be. So at the end of the day, you can use an expert judgment. There's a thing called elicitation that's actually rather nice, and it's really just kind of glorified guessing, but you can put it in a statistical framework. So so GUM mentions judgment, so that's good. What I say is I really don't like people who go through all the trouble in an uncertainty budget, get an answer, and then kind of add a bit to it just in case we've missed something, or just because it sounds a bit too low. That seems bad science to me. So I don't like the idea of you adding to your uncertainty budget if you've got absolutely no reason other than it looks a bit small. But on the other hand, if you can use your expert judgment to put numbers on possibly systematic effects, and that's absolutely fine, and you're allowed to do that. And there are ways of taking, as I say, something like a range and turning it into a standard uncertainty that you then put into your uncertainty budget. So I'm nearly finished. Let me just finish with just a couple of examples. So this is David Shaw's subcommittee, which I'm a member of. He looks after us very well. We're just about to publish the first general overview of consensus, how to get critically evaluated data, which is kind of would be a nice document. So look out for it. So a couple of quick examples. This is the Gamsjäger example of the solubility of cadmium carbonate in acid, whatever happens to it. And I took from that paper the Gibbs energy change. This is the data, 7 results. These are the stated uncertainties. These are the values. Just as a little aside, interestingly, this one here, number 2, actually fails a Grubbs test. So, and the authors of the paper say they'll leave it in anyway, because they can't really see why they should throw it out. It only just fails a Grubbs test, and they didn't. I don't think they even did a Grubbs test. I did. But I've put in this actual quote from Grubbs himself. Hopefully you've heard of the Grubbs outlier test. Actually, the rejection of outlying observations may be just as much a practical or common sense problem as a statistical one. And sometimes the practical or experimental viewpoint may naturally outweigh any statistical contributions. So please, and again, this is for students perhaps out there, don't rely on the statistics. Rely on kind of your own judgment. Use the statistics to back up what you think is going on. But don't do the statistics first and then use that to inform what did go on, as it were. So let that be a lesson to us all. So this is the answer. If you do a weighted mean, the uncertainty is 0.16 in 600, so that's not very, that's really good in a way. If you do Simonian and Laird, there's no dark uncertainty. And if you look at this, this is from the NIST consensus builder, by the way, say I recommend it highly. So these bars here are the uncertainties of each laboratory. And you can see that, you know, there's nothing left over when they've each got fairly large uncertainties. So there is no TOR to play with. The dark uncertainty is 0. And this is what the envelope looks like here. So this is what I was saying by essentially just adding up all of these Gaussians to give you some overall envelope, which allows you to pick the 95% range or what have you. And then of course you can work, if you know the 95% range, you can take a quarter of that to give you an estimate of the standard uncertainty. So in linear pooling, this is a much bigger value, and I'm not sure what's best. However, if you look at what Gamsjäger writes, the calculated uncertainties appear rather small, but are statistically correct, as we seem to follow a Gaussian distribution. That's not really the reason that there's a problem, but as we've seen, but never mind. Thus, the evaluators suggest to increase uncertainties to 0.6. So they've actually gone to all the trouble of working out 0.16, and this is in the paper. And they actually say, now we're going to use 0.6, i.e. 1% about of the figure. Well, perhaps that's nearer the linear pool value than it is the weighted mean. But it just kind of shows, you know, what problems you have, perhaps. Okay, last example. Apologies for going over the hour by a minute, but you know me, once I get going. Okay, here's Earl Waghorn's data. Got 9 data sets for the solubility. I had to find out what, you know, hexane dioic acid was. It turns out to be adipic acid, which I have heard of, in acetic acid. Different methods, turbidometry, gravimetry, and HPLC of saturated solutions. So it is quite likely there is going to be some dark uncertainty here, because each method presumably will be measuring something ever so slightly differently. So let's have a look at what we've got. We fit the data to the Van Hoff equation, as I explained. But unfortunately, each laboratory did their measurements at different temperatures. I mean, they're in the same temperature range, roughly, but not all 9 of them actually did the same temperature. So I couldn't take as an example one of their values to show you what I'm going to show you next. But what I had a good idea about was to take all of their fits. I fitted them, linear regression. I produced the uncertainty, which I've shown you how to do. So now I can create my own set of data from those 9 labs. I can choose a temperature. I'll choose 300 Kelvin. And this is what the 9 labs get from their own fits. And this is the uncertainty from their own fits. Okay, solubility at 300 Kelvin. This is the log of S. Using natural logs, obviously it doesn't matter if you use logs to the base 10 or natural logs, other than if you use logs to the base 10, you might have to have a 2.303 at some point in one of your calculations. So here we are, here are the values. This is them on the Disharmonian and Laird, which I did in a spreadsheet and then checked using NIST. So another good tip, if you're doing your own budgets, if you've got another way of calculating it, get a friend to calculate independently, or go to the website and use the NIST stuff and make sure you get the same answer, because there's so many ways that you can just have simple mathematical errors. Professors do it, so you will. Yeah. Anyway, these are the results. So weighted mean 0.3%. Desarmonian Laird now 1.8%. So the dark uncertainty at 0.05 is bigger than any of the uncertainties of each laboratory. So the dark uncertainty is the green bit, and the individual uncertainties are the blue bits around here. Or if you linear pool. Now, this is an example where I wouldn't say you should linear pool at all, because it's an absolute mess and there's no kind of middle tendency at all. In fact, what this is telling us is that we might consider chopping off these last two labs anyway, and perhaps just concentrate on these labs here and see where we get. I think this is some work for me to do in conjunction with Earl. But this again is another nice example of using it for consensus values. Okay, final. The Doug Moran Prize in Australia is an Australia-wide portrait prize. You saw the one on the first page that was me a few years later. This was, in fact, the first one he did, which also got into the finals. Again, looking even a little bit younger still, standing in front of I think it was a wall at Sydney University or something like that. Okay, let me just say, this is it. This is the last slide, again, with apologies for going on. Any uncertainty estimate is better than none. It really is. Just think about it. And because you do an uncertainty estimate, it does make you think about what you're measuring. And that's actually worth a lot, even if your uncertainty budget's a bit crummy. If you identify uncertainty potential sources, that's good too. So in cases where you've identified, you've got your measurement equation and you've got uncertainties for each bit of it, of course what you then do is you look at it and you realize that, oh, that's not worth worrying about, it's too small. Well, that also tells you that if you're trying to improve your experiment, you don't try and get a better way of fixing the temperature, because the temperature doesn't matter in this particular experiment. Look at the way that you measure something else. So looking at an uncertainty budget, and particularly a bottom-up uncertainty budget, if you've just averaged everything and you've just got a mean and a standard deviation, it doesn't tell you what the individual contributions are. So there's one good thing about the GUM approach, that it forces you and to understand where uncertainty comes from. Document your uncertainty budget. This is easy. You can, if you're doing a PhD, of course you can put it in your PhD. But these days, because we don't have to pay for the paper anymore, you can stick anything in supplementary information. So while in the main bulk of the paper you write plus or minus something, see uncertainty budget somewhere else, and as long as you say what you did there, because don't forget the definition of uncertainty. The last part of the GUM definition says based on the information used. So what that tells you is that you can have as many different uncertainty budgets as you have people willing to do them, because they each might use different information. And they're not better or worse than each other than you can look at the information that's used and say, you've forgotten temperature. Wow, what about that then? Or whatever it happens to be. Finally, don't do it all yourself. I mean, if you're a spreadsheet freak, then fine, you do it and away you go. But look, there's a lot of software out there. There's both proprietary software, there's free software. As I say, the NIST stuff is fantastic and correct. So both use their uncertainty website and also their consensus builder. And just use any validated software you can get your hands on. Validated, because actually these have been rigorously checked. If you decide you'll write your own little program, that's ever so nice, but how do you know it's right? So if you do your own stuff, you've got to validate it. I got some bullets, bullets in a body, bullets in the possession of a defendant. Supreme Court of Queensland 2020, after my evidence, the whole lot of evidence about bullets was thrown out, matched by ICP multi-collector mass spectrometry really well, but it wasn't a validated method. There are other problems as well, but if you can't prove that what you're doing gives you the answer that it should do, worry about whether it's right later, you know, then that's an issue. Okay, I think with that, I'm finally finished. So thank you, Simo, for inviting me, and I do apologize again for going on, but I hope somewhere in there, there's something of interest. Thank you.